Okay, so last time we started talking about a topic called optimization, and we looked at the one-dimensional optimization, right, last time, which is finding maxima or minima of some function f of x, one-dimensional function f of x. We discussed that there are different classes of optimization problems. There are optimization problems which are constrained. There are problems which are not constrained. What I mean by that? Let's just recap. Okay, so when we are looking for a maximum or minimum of this function, maybe that's the only thing which we are given. So someone tells us, find the maximum of this function, no other constraint. In some situations, we have some constraint. Let's say, find the maximum of this function, provided that there are some constraints, equality constraints, inequality constraints, right? For example, someone tells you, find the configuration of a bridge which has a minimum cost, but let's say given size, given width, so that you can fit certain number of lanes. That's a constraint. You want to find the configuration of the bridge which costs least amount of money, but at the same time it has certain size. So that's a constraint problem, okay? So you have a constraint. So we started with an unconstrained optimization problem in 1D. We were looking for maximum or minimum of function f of x. To be specific, we said that let's look only for maximum, because finding minimum of a function f of x is equivalent to finding maximum of function minus f of x, right? So to be specific, let's only look for maximum of some function, okay? Just to simplify the language. Because if we know how to find the maximum, we know how to find the minimum also. All right, very good. And we discussed two different methods. We looked at bracketing methods and we looked at open methods. And we discussed that bracketing methods, like in root finding, bracketing methods are a bit slow, but they are reliable. On the other hand, open methods, they can be fast, but they are not reliable. We looked at golden section method, which is an example of a bracketing method. And then we looked at parabolic interpolation method, which is an example of open method. All right, so today let's move forward and let's look at now multidimensional unconstrained optimization. Unconstrained optimization. All right, so to be specific, the methods which I'm going to talk about for multidimensional unconstrained optimization are, I will discuss in the case of two-dimensional functions. So I'll be looking at maximum of this function of two variables, function f of variable x and y. To be specific, like last time, we are making assumption, right? Assumption is such, for the moment, we assume that we have only single maximum, only one single maximum. One single global maximum our function has, to be specific. We are starting with a simplified case. All right, so we are looking at multidimensional case. We look at two-dimensional case. We describe few methods today for two-dimensional case. The reason I will discuss only two-dimensional case is because extending it to multiple dimension, extension of the algorithm itself is trivial, really. Okay, algorithm itself can be trivial extended. But what is not trivial in two-dimensional case is a geometric insight. When you're discussing into two dimensions, you can make some geometric insights like slope, you can draw. So it will be more pedagogical, more educational. Okay, so in order to explain the method, it's better to discuss in the case of two-dimensional function. Extension to multiple dimension is conceptually trivial. All right. Okay, so we're going to discuss two types of methods. There are two types of methods. Like in many situations before, there are two types of methods, right? Always there are two types of methods. One is called direct method or non-gradient method. Another one is called gradient method. Gradient methods. There are other names like steepest, ascent, or descent. Okay, and we'll discuss one method per each group, okay? We'll discuss one direct method today and one gradient method. That's the program for today. Okay, let's discuss, let's just mention what is the difference between these two. Difference between the two, the main idea is in the name already, right? Gradient, direct methods or non-gradient methods are the methods which do not rely on the gradient of that function. In other words, on the derivative of that function, okay? These methods do not require derivatives. They can do fine without derivatives. These other methods, gradient methods, as the name suggests, rely on derivatives, rely on gradient. All right, let's start with a really simple method which belongs to this class. And that method is called random search method. Random search method. And what this method does is already suggested by its name, right? Random search method. Random search method, okay. What's the idea? Let's try to plot this function. Let's try to plot this function. Okay, so I have my y coordinate and x coordinate, x and y. Okay, so let's say my function is given some way here, from some x lower to some x upper, and some y lower and y upper. Okay, so I'm looking at the function in some domain, like I usually do. Okay, so this is a domain where I will be looking at my function. Let's plot contours of constant f here, contours of constant f. One way we can visualize this situation, we have a function of x and y, right? One way we can visualize this function is this function can be telling us the height of a mountain at the coordinate x and y, okay? X and y are terrestrial coordinate, and f can be telling the height of that mountain, right? And you want to find where is the top of that mountain, right? So x and the y are your coordinates on the ground. X in this direction, for example, and y in this direction, and you have a mountain in front of you, and this function f describes the height of that mountain at each point, x and y. Okay, let's imagine like this problem. Let's interpret it like this. So we are trying to climb the top of the mountain. So in this case, these contours of constant f would correspond to contours of constant height, right? Okay, let's plot them. Let's say this is the lowest point. A little bit higher, maybe 10 meters higher. Maybe the contours of constant height is this, something like this. Then something like this, and we are approaching the top. Suppose this is the top position. Okay, so this is our mountain. These contours are contours of constant h, constant height. All right, what does random search method do? The idea behind random search method is extremely simple, extremely simple. And the entire idea is already suggested by its name. We randomly pick points in this domain, okay? We randomly throw points in this domain and keep checking the value of f. Let's say we throw 100 points randomly. We throw 100 points here and see which point corresponds to the largest f. That's the idea. That's the idea of this method. Okay? So how we can implement it in detail? In detail, we can implement it in the following way. Like last time, when we were talking about random numbers, we use pseudo-random generator, right? Computers have pseudo-random generator. Let's call R our pseudo-random number, which is coming out of a computer, and which ranges from 0 and 1, like in many random number generators, and which has a uniform distribution. In that case, we can pick points here using very simple formula, right? XL plus x upper minus x lower multiplied by r. And we can pick y like this, y lower plus y upper minus y lower multiplied by r, right? So we put random r's and we get random x and y, random pairs of x and y. So we can implement it by having a loop, for loop, which iterates over, let's say, some n numbers, and we generate n pairs of x and y, and then we find which pair corresponds to the largest f, which pair of x and y produces the largest f. And that will be our maximum. That's the idea. All right? Very simple, very simple. Now, as you can see, this method doesn't know anything about doesn't use any information about the function. Whether it has a slope, what kind of slope, what is the geometry, it doesn't use any of that information. It just blindly samples numbers uniformly. It doesn't even try to pick some region to put more numbers here, for example, because, I mean, if we visualize, we know that maximum should be here, so we can concentrate more numbers here. It doesn't even do that. It randomly, uniformly samples points on this domain. So it doesn't use any information about the geometry of that function. Because of that reason, it's a bit slow. It's a very slow method, really slow. On the other hand, though, one advantage of this method is that it can work with any function. It can be discontinuous, continuous, whatever. As long as you have a function, it will find. It will approach the maximum. Okay, you have a question?
What do you mean by uniformity?
Okay, by uniform distribution, I mean is the probability of that random number being in this interval as opposed to the next interval is the same. Okay, to be specific, let's say, so these random numbers are sampled uniformly between 0 and 1. Probability distribution function, specifically, to be specific, it means that probability distribution function is constant. What does it mean? It means that probability of having number between 0.4 to 0.5 and 0.9, 0.1 is the same, as long as the length of that interval is the same. That's what I mean, uniform distribution. Yes, do you have a question?
But is it reliable, this method?
It is reliable in the sense that it always works. No matter what kind of function you have, as long as you have a maximum, it finds. In this sense, it is reliable.
Only the case that it's going to be the maximum.
Okay. So if you want to really approach the maximum, you have to do a lot of iterations. So another way of saying it, it converges really slowly. Okay, if it converges really slowly. So this is one example of so-called Monte Carlo methods. Monte Carlo methods are methods where which rely on random numbers in order to solve some numerical problem. We'll discuss in more detail later when we will be discussing numerical integration about details of this method. For the moment, I'll just mention that. Okay, Monte Carlo methods tend to be slow for certain problems, and this is one example. Okay, you can show that Monte Carlo methods very often converges to the solution as error scales as 1 over n, where n is the number of trials. This is very slow function, very slow function. Okay, when we discuss the derivative, backward formula, forward formula, we show that in this case, error scales as of the order of h, right? Of the order of h. So let's think what it means in terms of this n. The corresponding n in this case would be, in that case, h would be is a size of your problem divided by number of points to which you divide this problem in order to solve it. So in that, even this backward and forward formula, which is further row formula, error scales as 1 over n, much faster than this guy. On the other hand, in this centered formula, it was h squared, right? As a result, you had n squared, which means as you increase n, error decreases really fast. Whereas here, error decreases as square root of n. It's pretty slow. That's the main drawback of this method. Error decreases really slow. But if you are patient, if you have enough resources, it will always work. That's a good thing about it. Okay? So I'm done talking about random search method. So let's move forward and let's talk about a gradient method. All right, gradient method. Now we're going to talk about a gradient method. And the method, specifically what we're going to discuss, is called steepest ascent method. Steepest ascent method. Sometimes it's called also descent method. When you are looking for minimum, it's called descent method. Since we are looking for maximum, sometimes it's called ascent method. All right, what's the idea about this? As I said, this method relies on gradient. So let's first remind ourselves what gradient is. Okay, gradient of a function, again, we are talking about two-dimensional functions. Gradient of a two-dimensional function is a vector, is this vector, which has the following components. X component is a df dx, and y component is df dy. This is this vector, all right? Let's discuss geometric meaning of this guy, okay? First of all, in order to do that, let's remind ourselves what is the meaning of derivative in one-dimensional case, okay? Let's remind ourselves what is a derivative in one-dimensional case. What is the geometric meaning of derivative? Okay, so, all right, let's look at some 1D case. So we have a function f of x, and the derivative of this guy tells us two things. First, it tells the magnitude of this derivative tells us the slope. The sign of this derivative tells us whether the slope is this way or that way. In other words, if this is positive, it means if you increase x, function also increases. If you decrease x, function also decreases, right? If derivative is positive. F and x. If derivative is positive, it's something like this, right? It's in this positive direction. Negative is something like this one. Positive derivative means that if you increase x, function also increases. So it means two things. Derivative gives you two information. First, magnitude of derivative is the steepness, how steep it is. Sign tells you direction. All right. This gradient plays a similar role, very similar role. It tells two things. It tells this function, this vector, now it's a vector. In two-dimensional case, we have a vector. So it tells two things. First, let's say I'm calculating the gradient here. First it tells is how steep here. Magnitude of the gradient tells me how steep in this equation. Is it flat or steep? Okay, if gradient is 0, it means it's flat. If it's non-zero, it means some steepness. Now, that's the magnitude. Vector, on the other hand, this is a vector. It means it also has a direction. It's pointing somewhere. What is the meaning of that direction? Meaning of that direction is the direction of the steepest climbing. All right? Steepest climbing. So two things. It tells me two things. Steepest climbing direction and the steepness at that point. All right, so in this gradient methods, it uses this information about the steepness and the direction of the steepest gradient in order to find maximum. Let's think how we can exploit that to find the maximum. Again, we are looking at the problem of mountain climbing. We need to reach to the summit, to the top of the mountain, right? Now let's try to think from that point of view. Suppose you need to climb a mountain, okay? And suppose you don't see where the location of this maximum is, okay? So it's foggy. Let's say you are trying to climb a mountain and you cannot see where it is located. It can be located anywhere. But what you can do, you can calculate the gradient here, which means steepness. So suppose I'm standing here, and suppose if mountain is rising in this direction, if it is rising in this direction, I know that I have to move in this direction, right? But the thing is that if I continue moving in that direction, do I reach the top? Really? What if top is here? It rises like this and then rises like that. Two values of what? Yes, x and y. So I'm moving in this direction. In this two-dimensional plane, I'm moving in this direction. So because here, right now, here, gradient tells me that I have to move in this direction. That's a local steepness, local curvature. And that can change, right? Mountains are not regular. They can have this complicated shape. So gradient here, direction of gradient does not necessarily point to the top. Which suggests maybe what we can do is the following. I can calculate gradient here, move a little bit, and after I move a little bit, calculate gradient again. If gradient keeps pointing in the same direction, I keep moving in the same direction. On the other hand, if gradient changes, suppose I move to this position and then gradient will be pointing in that direction, and then I start moving in that direction, right? So intuitively, if you think like that, maybe that should work, right? It should work. Now the question is, how much we have to move? How much we have to move before we calculate the gradient again? Any ideas? That's one option. That's one option. In a method called optimal steepest ascent method, what you do is the following. It's pretty clever. So I calculate the gradient here, right? And gradient is pointing in this direction. So what I do now, I create a one-dimensional problem, which is I define a function only in this direction now. Find its maximum and move to that point. And at that point, calculate gradient again. And that will be pointing in different direction. Create another one-dimensional problem, find the maximum there, and move like that until you reach the convergence. That's the idea. Okay? That is the idea. It's clear, right? Idea is clear. Now let's do the math of it. Let's look how we can do it mathematically. Okay, let's say that we start with a point called x0 and y0, right? Whenever we climb a mountain, we have to start with some point, x0 and y0. Very good. Let's calculate the derivative. Let's calculate the gradient. Okay? Let's say that we calculate the gradient at this point. X, I call it 0. To indicate that I'm calculating it at point x0 and y0. Okay? Or let me put it here. This sign means that I'm calculating it at point x0 and y0. Fantastic. Great. Now, let's define a one-dimensional problem. So I'm calculating derivative gradient here. It's pointing in this direction. So I want to create one-dimensional problem. Okay? How can we do that? First, we can calculate x and y along this direction. This is how we can do that. X is equal to x0 plus df dx 0 multiplied by h, and y is a y0 plus df dy at point 0 multiplied by h. Okay? If I so these two are components of gradient calculated at point x0, y0. Okay? If I calculate x and y like that, where h is some free parameter, this, okay, h is a distance from x0, y0 to some point along this one-dimensional direction. This gives me a coordinate of that point. Okay? So here I'm calculating derivative at this point, right? This is my x0, y0. Derivative tells me this is the direction. Gradient tells me this is the direction. If I move distance h in this direction, my x and y at that point will be these two. Okay, that's what it means. From here, x0, y0, I move by distance h, and that will be my x and y. All right, okay, that will be my x and y. Let me put this x and y into this expression. All right, what do I get? I get this. F of xy is a f of x0 plus df dx 0h and y0 plus df dy h multiplied by h. Sorry. What is this? What is this? This is not one-dimensional function. One-dimensional function because x0 and y0 are fixed, given. Df dx at that point is also fixed. The only thing which is not fixed is h. Okay, that's the only free parameter. So out of two-dimensional function, we created one-dimensional function along this direction. Right? So it's a g of, let's call it g of h. Okay, g of h. So it's one-dimensional along that direction. Now we can find the maximum of this function. We can use golden section method, which we discussed last time. So we can find the maximum. Let's call it h star. Okay, that's the maximum. This is where the maximum is. All right, now let's put this h star right here. Let's put h star like here. Okay, and let's call this guy x1 and y1. x1 and y1 is the corresponding x and y values where this function has a maximum. Very good. Now we calculate a gradient again, now at this point. So we calculate a new gradient at that point. Okay? And we do this thing again. Now we start from x1. Everything is calculated at point 1. Okay, and we create another function g of h, and we calculate its maximum again, and we repeat this thing until we reach the convergence. That's the idea. Any questions?
How fast it will converge?
Not very fast. It's convergence is linear. Okay, there are methods which converges faster. We are not going to discuss them, but this is a linear convergence. This method. Okay, so we just now discussed two methods, right? Two methods: random search method and gradient method. Suppose you use gradient methods, and suppose you find the maximum, or you arrived at a convergence. You converged. Now, how do we know what is this? Is it a maximum or minimum? Okay, so let's first discuss what we would do in the one-dimensional case. In one-dimensional case, everything is very simple, right? We are looking for a maximum of this function. So when we reach some kind of convergence, what we can look at derivative. It has to be 0, right, at that point. Okay, and we can look at the second derivative. We can look at second derivative if you can. We can look at second derivative. And second derivative, if it is larger than 0, what does it mean? Is it a minimum or maximum? It means that it's a minimum. If second derivative is smaller than 0, it means a maximum, right? In one-dimensional case, the situation is very simple. In the two-dimensional case, it's not that simple. Because you may have a thing called saddle point. In some rare situations, there is a thing called saddle point. Everybody knows, right? It's a saddle point. It's the structure in the form of a saddle. It's a saddle point. If you look in one direction, it can be maximum. If you look in the other direction, it can be minimum. So it's not a minimum, it's not a maximum. So, and the thing is that at the saddle point, if coordinate directions are aligned, you get zeros in both y derivative and x derivative. So that's not enough to judge whether you find the maximum or not. Okay, it's a little bit more complicated. And in that situation, people introduced a mathematical tool, in order to find out what do you have in that situation. Okay, and that's called Hessian matrix. This matrix allows us to analyze what we converge at. Basically, it's a matrix which consists of second derivatives of this function. Okay, notation is usually H, so it is a 2x2 matrix. Some of you know already. Okay, so this is a matrix. Second derivative with respect to x and y, and with respect to y. Very good. What is important in this context is a determinant of this matrix. Determinant. Okay, determinant will be this multiplied by this minus this multiplied by this, right? D squared f dx d minus okay. So the value of the determinants tells what kind of situation we have, it turns out. Okay. So first possibility, this can be larger than 0, and second derivative of f with respect to x can be larger than 0. Second situation, h can be larger than 0, d squared f dx squared can be smaller than 0. And third options, there are three options. This Hessian matrix determinant can be less than 0. These are the three situations. Okay, if you have this situation, you have a minimum, it turns out. In this situation, you have a maximum. And in this situation, you have a saddle point. Okay, so this is how you can judge whether you have a maximum, minimum, or saddle point. Okay, any questions? Okay, that's all I wanted to say for today. Okay, thank you.